sorry, before we start, did anyone lose his or her wallet? Sorry, but is that yours? Is that yours? Excuse me? Is this yours? Oh, yeah. Just open it.
Let's check it out just. Whoa! Wow! Fire! Whoa!
Is that a fireproof wallet?
Well, I didn't know, but
Well, just open it again.
sure. I didn't know.
Okay. Just check it out. Whose this is?
Well, there's a business card.
What? A business card? It writes, Ming-Dao iGEM team.
There's still something inside.
A carton?
A fireproof carton.
In June, there's an explosion at Taiwan's water park party. A fire extended all over the party, caused over 500 injured. What is fire? To build fire, you need 3 elements: heat, oxygen, and fuel. This is the fire triangle. As long as you have these 3 elements, you can build a fire. When it starts burning, it will release free radical and cause the chain reaction. Imagine you're at home, having dinner with your family. Suddenly, the fire alarm rings. Do you know how much time you have to escape? Several minutes, that's all you have. But what if you're in a house with fire retardant? You have much more time, 30 minutes. Maybe you even have time to pack your luggage. But the fire retardant we can see in the market are poisonous. When it starts burning, it exerts toxic gases because it contains halogenic elements and organophosphorus. The US EPA has confirmed if you're exposed to these elements, it is harmful to the human body. So you can choose. You want to be poisoned or be burned?
Okay, so as for me, I won't choose either of them. So there are 2 natural alternatives which comes from cows and sheep. The first one is casein, which can be found in milk. It is a protein that can be phosphor-related and contains 0.8% of phosphorus. So this fabric was coated with casein and was put to flammability test. As you can see, the fire didn't keep on burning. And the second one is wool, contains keratin with 15% of nitrogen. Compared to synthetic fabrics, wool has a better capacity of fireproof. Now you may want to know how phosphorus and nitrogen work to stop the fire. Let's go back to the fire triangle. Remove one of the elements, then the fire can be stopped. You can choose to extinguish the free radicals or cover the fuel, or to replace the oxygen with nitrogen. So while burning, phosphorus and nitrogen will both react to free radicals. As for phosphorus-containing compound, it will combine with the fuel and release water to form a cover layer on the top of the object. As to nitrogen-containing compounds, it will block oxygen and form an inner gas, nitrogen. So now you know the the two fire retardant biomaterials. And our team this year is to make fire retardant bacteria and to produce fire retardant proteins.
Okay, and now here is our approach. Our goal is to produce the phosphorus and nitrogen-rich protein, and we do it through the data mining, then gene cloning, and produce the fire retardant bacteria. Then we put it through the flame test to test its fire retardancy. And these are our steps to do the experiments. Let's start with data mining. Now we know that phosphorus and nitrogen plays important role in fire retardancy. So we want to get them as much as we can in the proteins. For phosphorus, in all amino acids, phosphorus were not contained originally, but it could be added in through the phosphorylation on serine, threonine, and tyrosine. And the phosphorylation on serine is the most common one, so we choose it as a source of phosphorus. As for nitrogen, after the analysis, we can see that arginine contains the most nitrogen. And here is the structure of arginine. We can see that it contains 3 amine in its side chain. And to do our data mining, we get the protein sequence from UniProt's database. Then we calculate the rate of each amino acid. After that, it's sorting and ranking. And finally, the manual correction to remove the predicted, unknown, or similar protein. And we got 3 top lists. And this is a program we use for the data mining. And this is the top 15 list of serine rates. We can see that the top protein is TPRXL. And this is the top 15 list of arginine rates, and the top protein is protamine B. Though the individual rate of serine or arginine is high, but we want the fire retardant ability both from phosphorus and nitrogen. So we add up their rates and rank it again. And this is what we got. The top 10 list of serine plus arginine rates. The top 2 protein, protamine P3 and TB16, are rich in arginine, but lack in serine. So we choose serine arginine-rich splicing factor 6, which is an SR protein, which is in the SR protein family as our target.
So what is SR protein? The SR protein is a family of proteins that are rich in serine and arginine. They are using RNA splicing, and their SR domain can help them on nuclear localization and protein-protein interaction. But which kind of SR protein should we choose? So we went to Academia Sinica to make Dr. Tang. And after discussion, we choose the serine arginine-rich splicing factor 1 and the SR protein kinase 1, which is used to phosphorylate the SRSF1. And this is the SRSF1 amino acid sequence. We can see there's lots of SR repeat in the C terminal. The SRSF1 consists of 248 amino acids. 43 of them are arginine, which means there are 18% of nitrogen, and it's higher than wool. 28 of them are serine, and there are 12 phosphorylated serine residues, and it's higher than casein. This is our matrix. We do the PCR check, the enzyme check, and the sequencing. And in order to get the best quality of the protein, we choose 2 commercial expression factors, GEX2T and ET29B, that are using protein purification. GX2T has a tag promoter and ligand repressor and a GST tag. And ET29B has a T7 promoter and ligand repressor and a his tag. Both tags can help us on recognition. To make sure that both of them can be replicated, we choose 2 different ORI and 2 different antibiotics.
Okay, so now let's take a look at our protein expression analysis. First of all, we transform E. coli BL21 as our bacteria, and we prepare it according to manufacturer's instruction. We made a stock, recover in LB overnight, and then dilute it 100 times, and culture it for 2 hours until the OD value is between 0.6 and 1, and then we add IPDG for protein induction. The method we perform for our protein analysis is SDS page followed by co-massing blue staining, and we have 3 groups. The first one is control, and the second one is SR protein, and the third one is SRPK kinase. On the third lane, which contains our SRPK kinase, we can see it is being expressed around its expected size, 93 kilodalton, and on lane 2, which is our SR protein group, we can also see that it is being expressed. And GST-free form can be found due to factors. So in order to specifically confirm SR protein, we perform a Western blot analysis to detect GST-fused SR. We use anti-GST first antibody followed by anti-rabbit IgG second antibody, and we visualize by DAB chromogen. On lane 2 and lane 4, which contains our SR protein, we can see that they are being expressed. And the shifted bands indicates phosphorylation by the SRPK kinase. And GST-free form can also be found. We did another Western blot analysis to detect His-fused SRPK kinase. We used mouse anti-His first antibody followed by anti-mouse IgG second antibody, and then we visualize it by BCIP chromogen. On lane 3 and lane 4, which contains our SRPK kinase, you can see they are being expressed. So after all the analysis, we want to make sure that our protein actually works. So we perform a phlegm test. And our phlegm test has 2 parameters. The first one is burning length. So we measure how much our sample is burned. So in this case, B has a shorter bar, which means it is less burned. So it has a better fire retarding ability. And for our second parameters, time of self-extinguishing, we measure the time interval from the sample catches fire to the fire dies out on our sample. So B also indicates a better fire retarding ability. So this is how we did our experiment. They are burning a sample, and some people think it's dangerous, so they're having a plastic shield. And this is our control group burning, and this is our bioconing group burning. So for our first phlegm test, we use cloth, and we have 5 groups: media, vector, SRPK kinase, SR protein, and phosphorylated SR protein. We burn it for 3 seconds, and we let it burn for 30 seconds. In this figure, you can see that phosphorylated SR protein demonstrates the best fire retarding ability among the 5 groups. And we did another phlegm test featuring cotton SR sample, and we also have 5 groups. And this time we burn for 2 seconds and let it burn out. In the first parameter, we can see phosphorylated SR protein also did the best among the 5 groups. And in the second parameters, it doesn't even catch fire.
So after testing on cotton and cloth, we do real flame test on house. In case you wonder how we do our real flame test, we cooperate with our school's fab lab and create those little wooden house that is made for burning. So this is how we do our fire retardant paint. First, we express them in E. coli VO21. We do bacteria culture and centrifuge them. Then we paint the protein on the walls of our house, and then we ignite them for 45 seconds. There are 2 groups in our test. One is uncoated, one is biocoated. As you can see, after burning, there is a thin char left on the outside of the house which is biocoated, and the other, without the biocoating, burns down to ashes. So, here's a quick summary of our project. First, we do data mining from UniPro database to find protein that is rich in nitrogen and phosphorylserine. Second, we build 2 biobricks, SR and SRPK, to phosphorate it. We express them in E. coli VO21. Also, we do 3 flame tests on cloth, cotton, and wooden house. And we found 3 characteristics: fire retardant, fire self-extinguishing, and fire resistant. Here's a quick highlight of our fire retardant biocoating. It's a novel of SR protein like casein or keratin. It is used as a fire resistant painting, and it was originally a proof of concept study. So, it needs purification before application due to safety issue. And now we're trying to apply for patent and transfer of technology. After all that things, you may ask, oh, I know your things are good, but how can that really improve my life? So here I'll show you some of our industrial applications. Did you know the market size of the fire retardant tool? The answer is 6 billion for fire retardant paint and 5 billion for fire retardant textile. So we found this company, Dila. It is a company which made fire retardant paint that can be painted on your furniture in the house. We pay a visit to them, and they show us their lab and their flame test. Also, we gave them a presentation about our project and promote our project to them. On the other side, did you know that spider silks are actually stronger than steel? Due to this reason, Craig Biocraft found a way to mass produce the spider silk because spider silks are lack in natural resources. And what they do is they genetically modify the silkworms to produce the spider silk. And what we want to do is to make fire retardant silk throughout this progress. So here we want to give thanks to our principal, our school, and our 3 advisors. Also to Dr. Tarn for her help and for the dry lab. This is our human practices. We have fire station, we have Mingdao, we have outreach, and a synthetic bio forum about GM food. This is our attributions. And here we want to show you something.
This is a tartan with our biotoken. And this is a normal tartan.
Did you get a chance to compare your fire retardant with what's out there in the market and see how it performed side by side?
We didn't print the market one because we think that's poisonous. So yeah, so we just bring our biocoat.
Did you get a chance to test them side by side? But back in that company you visited, they had little setups.
Oh no, we didn't do that because our protein needs to be purified. So we haven't purified it, so we can't just compare to their product. Yeah. Thank you.
So the protein you picked has a function. Are you worried about that function interfering with the host you're expressing it in? And if so, can you think of a way to remove its function?
You mean the function that the protein in the
The protein you picked has a function. It's a splicing enzyme. It cuts RNA.
mean, you're concerned if whether the function will interfere with each other.
Say it did. Can you think of a way to make sure you can still express that protein, but it doesn't cut RNA anymore?
We haven't done that yet, but because we only want the protein, so it can be fire retardant. So I don't think it really matters if you slice it.
Are you sure?
Because fire retardancy is from the SR proteins, phosphorus, and its nitrogen. So if we really it really do the RNA splicing, but it won't affect our product. Yeah.
You could change one base. You could change one residue and wreck its RNA cutting, but you can still have all of your residues to keep your fire retardancy.
So, thank you very much for this very entertaining presentation. I would like to know a bit how does it work, the algorithm for searching for this protein in the database. Can you give me the basic principle behind that? How did you access the database and what are the basic steps?
Data mining to find the protein.
Okay, to do the data mining, we read the sequence of each amino acid first. Then we calculate each amount of each amino acid and divide it by the total amino acid of the protein. And we can get the rate of each amino acid this one is the rate of the serine, and you can see that it's, and then we rank it through the Excel app, and we can see that it is the highest rate and the low rate.
So can you comment how long does it take to parse all the proteins that are there in the database?
You have about 500,000 protein, and the computer is fast, so 1 minute could down its process.
Thank you.
Great presentation. Was it important to actually identify a known protein, or could you just gone ahead knowing that you wanted serine and arginines and just synthesize a novel protein, basically?
So you mean just produce the SR repeat?
Yep.
Yeah, we have thought it before, but if we just make the SR protein out, because the science now, the technology now can tell us where did the SR protein start to be phosphorylated. So if we just make out the SR repeat, we can get the phosphorus. Yeah. So we just make whole of the SR protein. Thank you.
Hi guys, thanks for a great presentation. I was wondering, do you even need a protein? I think purifying is very expensive and time consuming. If you use just the amino acids, that might be cheaper. What do you think about that?
Just amino, you mean just use the amino acids?
Yes, just serine and arginine.
Because we think that SR protein, or just like the last answer, we need the whole SR protein to make sure that it's phosphorylated. Yeah. So we cannot just use the serine and arginine. Yeah.
Thank you. Thank you.
How do you know that your protein's not toxic?
I mean, when it starts burning, it is not toxic.
Or even before it starts burning, how do you know that it's not toxic to come into contact with it?
Okay, so we say I just mentioned that the bioreturn we can see in the market, it contains halogenate elements or organophosphorus, so it causes the poison when it burns. And in our bioreturn, it only contains the nitrogen and the phosphorus. So we believe that it is less poisonous than the viral retardant we can see in the market. Also, the study has confirmed when you burn the milk or wool, it is unpoisonous.
But how would you test?
We're trying to make the test with the college lab to test what is exactly contained in the gases when it's burning. Yeah. But we haven't done it yet.
I would suggest that you also think about the non-burning component, because your exposure will be longer. If you're putting it on chairs or pajamas or on a mattress, you're going to be more exposed to it when it's not burnt than when it is burnt. Yes?
Thank you.
Unless you plan on burning your mattress every night.
Thank you for your question.
Yeah, you guys did a great job prototyping